let's continue from the last lecture, right. So, we were basically looking at the conical flow at an angle of attack, right, and we it's been all talk. So, it's okay to get a little confused. So, hopefully, as we go along, you will try to visualize things a little better, and I will go on those lines again today a little bit. So, today also there will be a lot of talk, and then we will go on to the equations and stuff. So, hopefully, it should ring some bells by the end of it. Okay, so let us begin. Okay, remind us as what we did. So, this was the axisymmetric case, right, and so if I had a streamline like that, and this is what this is essentially showing is that it's going inside the shock structure, right. It's going inside the shock structure, which is the this red cone out here, right. And then I took another cone inside the shock structure, which is shown by this dark green circle here, right. So, this is a cone which you can think of that having the same vertex as this, but the cone angle is different, okay, for this say green cone. So, again, so the streamline, the way it goes in, right, it goes inside, and the streamline is basically traversing, right, into the cone. So, it goes in, and if I were to look at the projection of this, okay, onto this plane, onto the xy plane, then I would see it crossing it somewhere over here. Okay. So, the way we look at that is that if I take say to a line like that, okay. So, this point, it is the point that here it is crossing. So, you can imagine that we actually have a cone, okay, whose base looks like this green one. Okay. So, this point is actually crossing that particular cone, which is encased inside this red one. Okay. So, and if I look at that from this face, okay, so that gets projected onto somewhere over here. Okay. So, then again if I have one more cone, which is whose cone angle is again smaller than this green one, which is again you can basically see that we basically have 1, 2 and 3, and the fourth one is of course this is our actual physical cone. So, this cone again is encased inside the green one. It has a yet smaller cone angle than the green one, right. So, similarly, here if I draw these two, it is also passing through that. Okay. So, it basically what is happening is it is entering. Okay. First it enters, okay, through here through this shock wave. Okay. So, which is the red cone, right, and then it goes into another cone, it hits another cone of the shock, which is the green one. It goes further down and it hits the cone which is encased, which is projected at this blue base. Okay. So, basically I am looking at these 2 points, okay, on the these cones of shock that it is encountering. So, if I project this onto this face, they basically will project onto their bases. So, basically these 2 points, when the flow is moving from say the green cone, okay, into the blue cone. So, if I were to look at it from the xy axis, it would look like it is going from here to here. Okay. So, this is something that we have done in the last lecture. Just wanted to kind of remind ourselves. Now, again this is a streamline which is basically moving through the shock, and it is going on the surface of the cone. Okay. So, these are straight streamlines which are going on the surface of the cone. So, basically this for an axisymmetric case, you have the cone structure like that, you have the flow coming, and the flow equally diverges and goes past the solid cone here. Okay. So, this is what it looked like. Now, if we had to look at the this picture here, right, if I were to look at this picture, which is the, if I am basically looking through the base of the cone. So, this green portion is the cone, the red is the this shock wave. Okay. The blue is the slice that we were using, we are not using the slice here. So, I guess I could have drawn this without it. So, just ignore the blue here, if you will. So, if I were to look at this, basically I will get several lines like this, showing the traversing of the various streamlines. So, it will look something like this if I were to look from here through the base of it. Okay. Now, let us go to the axisymmetric case. Okay. So, axisymmetric case we said, so essentially this is with an angle of attack, as you can see, this is the direction of the free stream, angle of attack. Okay. Now, so we said there will be two streams, two streamlines, okay, one right at the top and one at the bottom, okay, and then the rest of the streamlines will basically behave like this. Okay. Let us discuss this a little bit more. Okay. So, let us discuss this a little bit more. Now, if what we see over here, okay, again, so this is my shock structure, this is my shock, and this is my cone. Okay. Now, and you can see this is the angle of attack. Now, let us consider basically two streamlines. One is at the bottom of this streamline, and another is top of it. The reason I do that is because, as I think we spoke about this briefly in the last lecture, is that because the shock, now the shock is asymmetric now. Okay, the shock is asymmetric about the this free stream axis line, and what you can see is that the angle of the shock, okay, the shock wave angle here is smaller than the shock wave angle here. So, the top part of this, okay, the top part of the shock wave is basically the weaker part of the shock, right. It is a weaker part of the shock, and this here is the stronger part of the shock. Okay. Now, let us consider this cone out here. So, we will, so when we say the cone, so this, let us consider these the topmost. So, if I consider two radial lines, how am I going to track the surface of this cone? So, let me consider two lines, okay, two radial lines, okay, from say here. So, if I consider say two radial lines from this cone vertex. So, one radial line is basically phi is equal to 0. Okay, you rotate that and take it to phi is equal to 180 degrees. Okay, okay, we'll come back to that. Now, so we are looking at, so this is say the topmost, the cone, the way the cone is projected here. So, this is the top version, the topmost part of the solid cone. This is the bottommost part of the solid cone, right. Okay. Now, in this case too, say for example, so what we are trying to do here is essentially again find out the projection, how the projection will look. Okay. So, again we have a streamline like this. Okay. So, we have this streamline which again comes in, goes inside into the shock structure and deflects out. Okay. So, say it at this particular point, say it look we are looking at this particular point. So, if I were to, if I look at the 3D picture, I see this streamline. If I were to look at just the projection of it, which is if I were to just look at the circled red, it would boil down to one point over here, isn't it? Okay. Similarly, if I have another another streamline here, so and it is moving like this. So, basically again I would look at this particular point. So, like we just did it for the axisymmetric case. So, if the flow is moving the streamline, so if I take 2 points from the streamline, so which is going from here to here, so this will result in basically 2 points here on the red circle, which will give us the direction. So, again these are basically radially. So, like the way we saw for the axisymmetric case. Okay. So, when you see this, so you will you can just imagine at this particular point an arrow which is pointing down. Okay, that will give us the direction in which the streamlines is moving. Okay, so these are typical streamlines which we have just seen so far. Now, let us consider, let us consider this, okay, one radial line which goes here, okay, and this is the phi here, okay, and what is this S1 now? Okay. Now, this S1 is the, so if when we have this flow, okay, the free stream, it comes from here. Okay, it encounters this part of the shock, the bottom part of the shock, okay, and we will have this, the streamlines in this particular case. Okay, so since here there is no symmetry, okay, it's not going to like nicely spread out. Okay, evenly spread out. It's not going to do that. So what we will have is that the flow here, we will have basically two streamlines, one going right down to the bottommost part of the cone, which is shown by this white dotted line here, okay, and we will have one more at the top. Okay. Other than that, what we will have, so let's at this particular point, let's say now, since these two, the bottom of the shock and the top of the shock are different because of the shock wave angle. So this is the stronger part of the shock. So at the end of the day, what this means is that this has, when my flow will encounter the shock, go across it, it will encounter say an entropy change of S1. Okay, it will encounter an entropy as S1, and if I if I for example look at this radial line here, okay, so this is a radial line which is emanating from the vertex of the cone and going on the bottommost part, or phi is equal to 0, it is like phi is equal to 0 line on the surface of the cone. So now this, so if I am looking at the surface of the cone, so this projects onto the base of the cone as just this point, isn't it? If you were to look at this particular line from this face, if you just imagine that at this point, just try looking at this from this face. So this projects, this white line here projects onto this green base at this blue point here, okay, at this particular point. Similarly, we will draw the other radial line which is basically going from the topmost part of the cone, or the phi at the radial line at phi is equal to 180 degrees. Okay, and again this encounters, so this here the change in the entropy is basically S2. Okay, and again if I project this line onto the base of the cone, we basically encounter this. It basically projects as a point, which is this blue point. Okay. So now that's all there is to it. That's all as far as the straight streamlines are concerned. That's it. Okay. Rest everything is curved. Okay. What do I mean by that? So like I said, you have the flow which comes in. Okay. And you have one streamline going right down at phi is equal to 0 part of the cone. You have one more going at phi is equal to 180 degrees. Now rest, now what will happen is that there is the lower part of the cone here, the lower part of the shock structure over here. Okay, so that is facing basically the free stream, that is called the windward side. Again, using, I think, if you can think of a mountain and there is flow coming in, it's facing it directly. Okay, so if you can think of that, even when you think of that the flow will actually move past the mountain onto the other side. That's exactly what is going to happen here. So you have this cone. Okay, so the flow comes in. Okay, enters through the shock, reaches the bottom of the cone surface, and then curls around and goes up to the top. Okay, and that all these streamlines are say are curved. So if you look at this, I draw this dotted line here. Okay, I have drawn this streamline here, part of which is dotted, another is solid. what this means here is that this part of the curve, which is the dotted one, is going inside the shock wave, right, is going inside the shock wave, and then it goes from the bottom of the cone and curls around and goes to the top, and then it tries to merge over here at this particular radial line. Now, as we said that when it goes through this shock, okay, it encounters a entropy of S1. So, it will go from here and have an entropy in S1, and then it go and curl up and go here. Okay. Now, before we go and try and understand all of that, let us see how this would look if I project it onto the surface of the cone and the shock. Okay. So, if I were to look from here, so now when I look at a 3D picture, I see a curved a curved streamline going like this. Now, if I look at this whole picture from this end, if I am looking into this green base right through here, then what would I see? Okay. Just pay attention to this. So, if just think of drawing several radial lines which intersect this streamline. So, where do you think that will project onto when we think of this base? So, just look at the solid part of the streamline, which is on the surface of the cone. So, now various parts of this. Okay. So, now pay attention to this this surface. So, pay attention here. Okay. So, if you see this, okay, so then these are various parts of this streamline which project onto here, and you can see the top portion here. Okay, the top portion here is merging with this line. So, the end of it will also project onto here, which will be again this line. Okay, this will be again this line, and this will actually merge with the blue circle here. So, this line should actually merge with this dotted line. Okay. So, I am just putting it on the side here to distinguish here. Okay. But let us understand that this is actually the same point. It should actually sit on top of this. Okay. So, that is how the solid portion of this line projects onto the surface. What about this? Now, this part will basically project onto here, this red part of it, isn't it? So, if I do that, now look at this red, concentrate on this red circle here. So, if I do that, so various parts will look like this. Okay. So, let us do that sort of again. So, we have say these streamlines, and we have these streamlines, then we have this. Okay. If you look at this line which is going here, now look how does this project. Now, look at this blue the green base now. Okay. So, that is the S1, and then so this is how it projects. Again, look at the top portion of the cone, phi is equal to 180 degrees, concentrate there. We have a line like that which is S2, okay, and then this projects onto the green base as this blue line, and then we would have a streamline which is like that. So, for the solid part of it, again concentrate on the green base. So, you see various parts of it, they will project as small points like this, and the end of it emerging with the phi is equal to 180 degree radial line. So, therefore, if you concentrate here, that also projects as a small point, right. And this part of it again, this part of it, it will project onto the red base. So, let us do that again. Okay, that's it. So, now obviously, we will have several other streamlines. Okay. So, if I do that, let us just look at this space here. So, okay. So, you have these particular streamlines. Okay. So, all of these are going through the shock wave, and then they curl around from the bottom of the cone up to the top. Okay. And the bottom is essentially the bottom is the windward side, and the top is the leeward side. Okay. So, now how will this look if I on the projected plane. So, let us look at that. Okay. So, okay, we will discuss this various points of it. Okay. And a lot of the time the discussion will entail on a comparison with the axisymmetric case, and I don't know if that's the best way to understand this, but sometimes we can draw some inferences. Okay, so so this is a shock structure here, okay, and this is the cone, the green one. Okay, okay, let's look at this now. Now this line, okay, this line, what is this line? This is nothing but this streamline over here. If you look at this, if you project this onto it, so these points are the ones which are on the surface of the cone, which is what is shown over here, and the remaining of it are in the shock, which is over here. So if you look at this in the projected plane, then it will look something like this, this particular streamline. Okay. So similarly, we will have other streamlines, of course, which will look like this, and what we see that all of these streamlines, obviously, as you can see, they are going through the top surface, which is phi is equal to 180 degrees. So they generate at various points, but they all converge at phi is equal to 180 degrees. So and all of these points project at the same point, right, same point here. So they are all going through this particular point. Okay. So again, so these will be the like I said, these streamlines, which we will know. So I am just drawing a couple here, so you can see that we will have several streamlines which will project on, we can see the projection of that here. Now again, if I look here, where do these 2 points lie? Okay, these 2 points. So this blue point actually comes here, and this blue comes at the bottom over here, right. So if you look at this, okay. So now, what is the issue here? What is the problem, or what is not the problem, or so on and so forth. Okay. So now let's sort of discuss this a little bit. Okay. Now I don't know if you're already seeing this. So like we said yesterday, a particular streamline, okay, a particular streamline will have a single value of entropy. So when the streamlines, okay, which are generating from here, which are generating from the bottom or the windward side of the cone and moving up on the surface of the cone. So this is encountering an entropy S1. So all these streamlines out here, that you see have an entropy S1. Okay, entropy change of S1 as they go here. Okay, and these streamlines go ahead and converge on the top. Okay, now this streamline also, this dotted line which is going along the surface, okay, this also has a entropy S1, okay, because it is moving in from the vertex, okay, and it's going along the surface of it. So it is on the windward side, okay, of the shock as well. So this will also have an entropy S1. So on similar lines, the line at the radial line at the top of the cone at phi is equal to 180 degrees will also have an S2. Okay. Now look at this. Now look at this over here. So these streamlines, okay, these streamlines have an entropy of S1. Okay. And when it comes and converges on this particular line, so if you look at this blue point and this white point, okay, now the blue point is a single point, okay, which is the same streamline, so to speak, each has an entropy of S2. Okay. But when these streamlines come and join these, they have a streamline, an entropy of S1. Right. What does that mean? That we have now, when these are joining here, we have a single straight line which does not have a single value of entropy. It is actually multi-valued. So these streamlines, when they come here, they have S1, and the streamline which is here, riding along the along the body of the cone has S2. And they are all converging at phi is equal to 180 degrees, and they are all projecting onto this particular point here. Okay. So we have several points there. If you look at just this point, okay, you have several points there. Okay, you have several small such projected points, but all of them, although they are the same location, they do not have the same entropy, right. So, these points have S1, these points have S2. So, clearly this is a singularity. Okay. So, this point is therefore, and then this line, okay, is there, this line is therefore called as vortical singularity. Okay, vortical singularity, okay, I'll probably go to the board in a while and then sort of write that out. So, this line is actually a line of vortical singularity, okay, and it projects onto this point here. So, you can see that this point onto the projected plane here, okay, is the point of vortical singularity. Okay. Also notice, okay, also notice here that the shape, shape of this projected plane is not any more concentric circles like we did in the axisymmetric case, right, isn't it? Because the shock structure, as you can see, is no more, the shock structure is no more like symmetrically located about the cone if you look from here. Okay. So, that is why we have this little pout on the top for whatever. Okay. So, now all of this, okay, so all of this that we see here is basically when the angle of attack is less than half of the cone angle. Okay. So, this angle is the half cone angle, and the angle of attack is less than the half cone angle. So, what we are seeing over here, okay, what we see over here is this is basically the case. So, we on the top portion, on the top of the cone, if you look at this, okay, so this is the projected plane, etc., we have a vortical singularity point over here. Okay. So, let us go to what happens if alpha, the angle of attack, is greater than the half cone angle. What happens then, right? So, we are looking at the same picture. Okay, this alpha is just greater than the half cone angle. It is the same picture. So, again we have two radial lines, phase 0, phase 180 degrees, and we have these streamlines. Okay. So, again the entropy change there is S2, entropy change here is S1, say, okay, and okay, all right. So, now what we will look here. Okay. So, here if you, this is S2, okay, and this radial line, again it projects onto this point. Now, let us look at one streamline. Now, this streamline in this particular case, it comes from here, which is S1, it is S1 here, but it does not merge onto the just exactly the top of the cone. Okay, because of a larger angle of attack, this does not merge exactly onto the line at the top of the cone. Okay, basically it does not merge onto the phi is equal to 180 degrees line, radial line. Okay. So, similarly we will have the other streamlines which again do not merge, okay, but they do merge somewhere, they seem to curl up and then they do merge somewhere, and if I draw a line through that, I will see that this is so there is merging onto a line which is not coinciding with phi is equal to 180 degrees. Okay, that is happening because the angle of attack is greater than half cone angle. And again this straight line that I just drew is a radial line, will have an entropy of S2. Okay. So, this line in this particular case is also a point of is also a line of vortical singularity. So, compared to the previous case, okay, in this particular case this line of vortical singularity has basically moved from the surface of this cone and above it, right. And now, if I look at this picture, okay, and look at the base here, so that projects onto, so if this particular thing, okay, it projects, it does not project onto the surface here, but it is somewhere above it. Okay. Think of this, and if I extend this line, so then I will be looking at it from here. Okay. It is projected somewhere over here in the flow field. So, it is now into the flow field. Okay. So, therefore, if I look at this if I look at this particular picture over here, so again we see a sort of this is the shock wave, and you can see that it is even more skewed, or the asymmetry is increased with the increased angle of attack about the cone. So then here this is the streamline, which is this one. Okay, this is the streamline. Okay, this streamline is above. It is no more on sticking onto the surface of the cone. So now that it is above. Okay, so then again all these streamlines pass through this. So again we will have similarly all these streamlines which we learned before, and therefore we will still have this point here, but the vertical singularity point will actually be lifted off the surface of the cone and somewhere over here. So if you can see this picture over here, right? So this line is basically projected onto this point here, and that point, if I look at it from here, it's actually at this location. So unlike in the previous case, for the alpha less than half cone angle, the vertical singularity point was here on the surface, right? Now it has lifted from here to here. Okay, so what we can see, okay, from of course both these pictures, okay, what we can see from both these pictures is that we have several streamlines. Okay, we have several streamlines which are converging at this particular point. So there is a dense mesh or array of streamlines passing through this particular point. Okay, and so which means what? If I have a lot of lines passing through this, so there is basically a large gradient of entropy which is at this particular point. Okay, going through this particular point. So the entropy change, okay, is pretty large. Therefore, when the streamline will go near the surface of the cone, okay, because of this region, because we have so many streamlines, okay, converging at that point. So this entails that we have a significant finite change in entropy if we look at this. Okay, so well, that is something I want to discuss. Okay, now there is something else here. For example, in this particular case, okay, v theta and v phi are finite. Okay, so v theta and v phi are finite. Okay, and at a particular location anywhere, okay, in the flow field, we will have a certain velocity which is given by the component of velocity which will come from v theta and v phi. So let us just sort of go to the board and write out and see. Okay. Okay, so anywhere in the flow field, right? So we will have, say, okay, I'm not drawing any pictures here. I think by this time okay, where's the v phi and v theta. So the total velocity, okay, I'll just think of this velocity component which is given by this. Okay, so we have a velocity component which is given by this. Okay, now if from the pictures that we just saw, okay, when we have the streamline which is going, we have this cone, say, okay, this is my cone, okay, and we have the shock wave, like that. Okay. So, we have these streamlines, okay, which come here and go right, down here. Okay. So, right down here, okay, we have, say, this particular streamline. Okay. Now, if you look at another streamline which comes from here, what will happen is it will enter the shock wave, then reach the surface, and then it will curl up. It will curl up. Okay. This will be a curved line. It will curl up. Okay. So, you can think that, of course, so it is curling up. It is changing its phi, it is changing its theta. So, it has this streamline, for example, has definitely a finite, velocity here. But look at this streamline. Okay. Now, this streamline is not curling up, it is just going straight onto the surface of the cone, moving along it, and it does not change its theta, does not change its phi, isn't it? So, which means that the phi, v theta and v phi is 0, which means the velocity is 0. So, for this, this velocity here is 0. So, if you project it, therefore, if the point that we are projecting onto the face, so if we look at the projected point here, okay, onto the cone surface as we were doing. Okay, if I look at this, so this point projects onto here. Okay, this. So, we can therefore, in this particular case, say that this is a stagnation point. We can call this as a stagnation point. But however, if you look at this, okay, the velocity, this streamline still has a velocity in the radial direction. So, Vr is finite. Vr is finite, is not 0. Vr is not 0 for this particular streamline, but V theta and V phi is 0. So, we can say it has this is like a stagnation point based on this velocity, but truly there are really no stagnation points in a 3D conical flow, if you see from here. So, for these, of course, there are it is positive, it is finite, okay, the velocity is finite, but even for this radial line, the it still has a finite Vr. Okay, it still has a finite Vr. So, typically speaking, or in a 3D conical flow, there are no stagnation points, but you can think of this as a stagnation point over here, and this goes for all the cases that we have seen. Okay. And since we are talking about velocities over here, okay. Now, if this velocity of the fluid, okay, moving through of the streamline moving through the shock structure onto the cone, etc. Okay. So, if this velocity, okay, is greater than the Mach number, okay, if this becomes let's just say the corresponding Mach here, okay, the corresponding Mach number, okay, this v. So, if the velocity of speed is a, so v by a. Okay. So, the corresponding Mach number is supersonic. So, if we have supersonic, okay, the velocity here, okay, if I have supersonic velocity here, so I will end up having embedded shocks. Okay. So, say for this particular streamline, I have a supersonic velocity, which is say v or say for this Mach is greater than 1. Okay. So, within the shock structure, we can have, if you consider several lines, so you will have a series of shock waves. Okay. We will have series of shock waves, and this sort of, so Mach number. So, now this sort of a case will happen most of the times when for the alpha greater than half or say theta c. Yeah, actually, well, I cannot draw it here. So this is my theta c. Half cone angle is your theta c. So this this embedded shock thing will happen most of the times when for a very high angle of attack. Okay, so a very high angle of attack will end up in increasing the this velocity, and then if this becomes supersonic, we have these embedded shocks. Okay. And okay, so like I said, now this line, let me just write it out so that you kind of understand what I'm talking about. So this straight line here is a line of what we say vertical singularity. So if I had to write it out, it is singularity. Okay, so this is essentially vertical singularity, these lines. Okay, one more discussion before we finally stop. Okay, this cone, whatever we have studied so far, is right circular, isn't it? We have a right circular cone in the sense that if I project it, I essentially get a circle. Okay, and if you drop a perpendicular from the vertex here, it makes 90 degrees with this. Right? It's a right circular cone. That's a right circular cone. Okay, it doesn't have to be like that always. Okay, it doesn't have to be like that always. You could have this projection as an ellipse for that matter. You can have that as an ellipse. Okay, and in that particular case, now if I do have an ellipse of that sort, okay, now if we do have that, now even for an axisymmetric case, okay. When we have an elliptical projection of the cone, there will be two independent variables. There will be theta and there will be phi. Unlike if you have a right circular cone where the phi is the phi doesn't, like del phi doesn't matter, or v phi is 0 for a right circular cone. For an axisymmetric case, okay. So let us look at this. So if I have a right circular cone, okay, I have a right circular cone, right, and I have an ellipse. Okay, so here for axisymmetric case, right, we have just one independent variable, which is theta. Okay, but for the ellipse, we still have theta and phi. I think that is understandable, isn't it? I think it's easy to, by the time if you look at the geometry, try to look at it, think of that as an ellipse instead of a circle. I think this is kind of intuitive. Okay, so therefore, even for an axisymmetric case, in the sense that the axis of the cone is in line with the free stream, we still have a 3D flow when it comes to ellipse. Okay. Okay. One more thing before we sort of close with this. Okay. Now, if we've done basically an inviscid analysis over here. Right. So now for this particular case, now if you come from here, okay, this is the right circular cone that we've been doing so far. So now we have the flow which comes here, then it curls up and it goes onto the leeward side of the cone. Let's call that, this is 180 degrees. Here phi is 0. Okay. Now, from experiments, okay, when we have done numerically inviscid analysis here, okay. Now, when experiments show that kind of match with our numerical findings, okay, because this portion of here is also inviscid. Okay. However, when we come on this side of it, okay, when we come to the leeward side of it, there might be flow separation at that, at this portion of the cone, right. So, therefore, here an inviscid analysis may not be sufficient to predict the properties or predict what is going on in around this region. Okay. So, I think that should be sort of all that regarding this. Okay. I think that should conclude, and what we will do now is essentially go and look at the equations, okay, and see if we can make some headway into the way we found out a method, using the Rogue-Cotta method. We solved the Taylor-Markov equation to solve for properties between the shock wave and the surface of the cone. Let's see if we can do something like that for a 3D case, and does that make it more complicated? If so, how much, so on and so forth. So, we will deal with equations and stuff when we start our next lecture. Okay. So, this is a little bit on the trying to visualize, okay, the 3D picture out here. Okay. So, 3-dimensional and some of the issues which are associated with this. Okay. So, I think that will be all, and we will take it up from there. Take it up from here next lecture. Thank you.